Greetings. We are a team of University of Puerto Rico engineering students, and we are presenting today the Earthquake Alarm Project. Our team is composed by Kevin Rivera, Marcos Felix, Jorge Ortiz, and Johnny Santiago. We will each take turns presenting what we did, how we did it, and the results we have obtained in the project. Greetings. I'm Kevin Rivera, the software development lead for the Earthquake Alarm Project. My main objective for this project was to develop the system software and integrate it into a working system. I achieved this by implementing a modular software architecture. With this approach, I was able to add, troubleshoot, or remove pieces of software without significantly affecting the overall performance of the system. This is the system software architecture for the alarm. When the system starts, it initializes the sensors, the peripherals, the communication modules, the data logger, the input and output pins, and the clock. Afterwards, it runs an infinite loop with scheduled events. The first scheduled event is to read the sensor. When reading the sensor, it'll check to see if the reading exceeds the boundary value, which is the sensitivity set by the user. If so, it'll turn on the alarm, log the data into the SD card, notify that a seismic event is occurring, and display that seismic information in the LCD. The other two scheduled events are to change the sensitivity. The user has the option to change the sensitivity via the app or through the system with the buttons. If it changes the sensitivity, it'll display the sensitivity change in the display, and it'll also display it in the application. We have the user interface for the application. The user will be able to see the information of the last event, such as its magnitude and its graph. It will also be able to see the sensitivity that it has chosen, which by default is 3, and will be able to change it with the sensitivity change button.
Greetings, my name is Jorge Ortiz and I am the hardware development lead for the Earthquake Alarm Project. My main objective in this project was to find a way to incorporate our prototype concept into a single working system. This is because we based our initial design in the form of modules, but we wanted the end user to experience a system that is reliable but also that is easy to work with.
One of the first contributions that I made in this project was to incorporate a data logger. This was done so that the alarm have the ability to record important seismic events data, like for example magnitude and time, for later analysis. Because we base our project on different modules, with the help of my colleague Johnny Santiago, we began our research to recreate those modules based on our needs and using a schematic design software. We did this by looking mostly for open source information of schematics, datasheets, but also implemented techniques we learned throughout our years of study on our university. Once we figured out all of the components of our final design, all of them were integrated into a single PCB design, which it is no larger than the size of an average smartphone. Because the system is made to measure an unpredictable event of nature, a power backup system was incorporated in case the main electrical source in the area is compromised. Finally, once we received our PCB design, we made some final solder adjustment, tested and corrected some design limitations to have a complete, robust system that met the expectations we had from the beginning. Now, with all of this done, we had a system that was ready to be validated.
Hi, my name is Johnny Santiago, and I am the design leader of the alarm case. Now, I will tell you a little about its characteristics. We decided to build our enclosure that separates the circuits from the outside environment with the Fusion 360 program. It has a length of 215 millimeters a width of 105 millimeters, and a thickness of 50 millimeters. It is made up of two covers, which are connected by a grip configuration and by placing a screw at the top and at the bottom of the case. For the front cover, we made the holes so that it looked good aesthetically and where we could place the LED screen, the buttons, and the LED light. For the back cover, on the outside, we made the holes where we can access the SD card slot, the micro USB port where the system will be powered, the switch to turn the system on and off, a hole to reset the system, and a box to place the battery holders. Inside, we designed some cylinders where the PCB fits perfectly, and a configuration on top of the battery holder box where the buffer will be placed. It was designed for an easy and optimal assembly for its manufacture, being able to assemble everything from above perfectly, as you can see in this demo. This is how the case looks physically. We use white PLA for material and a 3D printer to create it. And finally, this is how it looks like, fully assembled and put into operation.
Hello, my name is Marcus Felix, and I will be speaking about my role in the project. My role consisted of studying earthquake phenomena, studying the different types of methods used to determine a magnitude of an earthquake, and validating the project. Well, simply, earthquakes are produced by slips in the Earth's tectonic plates. These slips produce different types of waves. The two types of wave produced would be P waves and S waves. P waves are more analogous to sound. They propagate via compression, decompression of the Earth's crust, while S waves are more analogous to a rope moving in space or a guitar. They are more transverse in nature. So the problem arose, or our main problem would be, how do we measure these waves and how do we use this measurement to determine the magnitude? Well, here's where lies our first problem. To determine the magnitude of an earthquake, multiple accelerometers will be needed, so the different times that the earthquake shock would get to an accelerometer, during that difference in times could be used to determine the epicenter of an earthquake. However, since our device only consists of a simple accelerometer, well, this task will be impossible. However, intensity can be measured locally. So this is why, for this reason, we use the MMI, or better known as the Modified Mercalli Intensity Scale. This scale can be measured locally, as I said, and there are many relationships between peak ground accelerations and this intensity scale. So we can use accelerometers to determine the intensity of a local vicinity. Using the PGA provides to be very useful for us and the team, since PGA reduces the complexity of the ground movement of an earthquake to a more simple in nature. The PGA does not take in consideration duration, the spectral content, or the resonance that may occur that may affect our value of intensity. On the other hand, MMI also takes into consideration the human description and the subjective nature of the response of a human during an earthquake. So we believe it's an ideal equation, it's an ideal relationship that we can use for this project in particular. The relationship we obtained was from the University of Costa Rica. There are many relationships that relate MMI and PGA for different regions around the world. There are relationships for California, for Japan, and even Southern Europe. However, we chose Costa Rica since it's closest to Puerto Rico and it approximates better our conditions in the island. Finally, the validation process consisted of using a Quanser shake table to simulate the movements of an earthquake. The earthquake we used in particular was an earthquake that occurred in Northridge, California some time ago. Our steps consisted of first, modifying our equations so that they could fit, so that the accelerometer we use can work seamlessly with the equations. Next, we placed our accelerometer securely on the table with tapes and other different methods. And finally, we compared the data between the theoretical data between the accelerometers in the Quanser table with the accelerometers in our device. Then we plotted this information in Excel and see how our runs were going. We calculated different types of data. We calculated percentage errors between MMIs, theoretical and experimental, and we calculated different types of accelerations that occurred for different types of magnitudes of accelerations. And this is the way we validated our project.